So welcome to this talk. Today I will present the M4 project, which is a collaboration between Sound Medical Decision, AstraZeneca, Linköping University and Tissues. We are a team with a wide set of different backgrounds. We have pharma researchers, experimentalists, biologists, biomedical engineers and mathematical modelers. Together we are collaborating, giving each other insights on our corresponding tasks. We are coordinated into different sub-projects. For instance, 2 days ago, Katarina Schmeck had a poster of their work at Tissues. Yesterday, Lisa Wilén had a presentation about their work at AstraZeneca. And today, I have the presentation of how we utilize mathematical models. So together, we are working towards knowledge-driven and efficient drug discovery development by using mathematical M4 models. The project started with us identifying that today's drug development is associated with long durations, high cost, and a large need for animal experiments. So we believe advances in microphysiological systems combined with mathematical M4 models, we can improve these shortcomings and create efficient drug development, where we create quicker, cheaper, and more ethical drugs. The term M4 is something you will hear throughout this presentation, and it stands for our type of mathematical modeling, which is mechanistic, multi-level, multi-timescale, and multi-species models. The mathematical model we will look at today consists of about 40 different equations that are all in one way or another interconnected and dependent on each other. And it's very important for us that these equations are not just simply equations, but it corresponds to true biology. Each equation is partly dependent on system constants that we call parameters. And when we introduce a new parameter into our model, we first look at what it represents, biology, then we look into clinical data and calculate an interval for what is physiologically reasonable for this variable to be. We then train our mathematical model on the real-life model, so MPS. And with that training, we then have a digital copy of an MPS, where we can play around and study digital cells. And we can simulate future MPS experiments, optimize protocol, change media compositions and drug concentrations. And we can also simulate previous experiments we've done and predict unmeasured variables of those. So with our model, we get more out of our MPS experiments. So this combined MPS with M4 modeling is done in our M4 project, where we work towards a knowledge-driven drug development pipeline. Here, we integrate partial insights from MPS, animals, and humans into an interconnected and big picture with our modeling, with a feedback loop to clinical and preclinical phases. In the central of our work is the MPS, where the experimental cost is lower compared to the other systems, and its metabolic flexibility is great. So we want to be as dependent on the MPS as we possibly can. So we use the MPS to study organ-organ crosstalk, and also we can isolate different organs' contribution to the metabolism, which naturally isn't possible in vivo systems, at least not ethically. To the right here, we see illustration of the SHIP2 that we use in tissues. So we have an on-chip micropump that pumps the media through a microfluidic channel, which recycles the media, and it goes to 2 different compartments where we have pancreatic and hepatic cells. In some experiments, we also take out the liver and only study pancreas, and vice versa. So we investigate the metabolism using MPS in regard to glucose homeostasis, cell functionality, disease progression, pharmacology, and pharmacodynamics. Our experimental planning is based on the metabolic question, and in this planning phase, we use existing knowledge and in silico testing to optimize our protocol. The experiment is conducted either at AstraZeneca or Tissues, depending on what equipment and what cell is needed. And thus, our experiments are done at 2 different labs, and thus we believe we have great reproducibility in our work. We then, together, analyze the data, answer the metabolic question, we expand our current database, and in this expansion, we drive the M4 modeling development. So with an expanded current database, a validated or more complex mathematical model, we are now ready for another cycle of further drug development and increasing our metabolic knowledge. One important thing in our work is to understand the cell's functionality in vitro and how it corresponds to in vivo functionalities. So we have looked at many things, and among them we have studied insulin resistance development. So in this figure we can see glucose and insulin concentrations in the MPS media, where the error bars are data and the colored line are computer simulations, where the area is the model uncertainty. Every 2 days, the media is changed to 2 different glucose levels. So we can see here that the red color, the glucose levels are high glucose level, and the green group is to a healthy glucose level. Please note also that the insulin concentrations are reset at each media change. Please note there is a change in glucose utilization over time. This is partly described by the model as we have a decreasing pancreatic functionality. But this doesn't tell us the full story, because if we look at the last media change here, we see slightly higher glucose utilization in the green group compared to the red group, both in data and simulation. And this is described by our team and our model as developed insulin resistance. So in order to fit all data used for model training, not only this data, the model will predict how this insulin sensitivity behaves. So here we can estimate and predict insulin sensitivity using our model. So here we see at the first media change, the red group started to develop insulin resistance already at the first media change, while the green group remained completely healthy until the last media change, where both groups were submerged to the same amount of glucose, and thus we see this drop in insulin sensitivity. So in conclusion, we can investigate the development of insulin resistance in our chip. We have looked at many different things. We have, for instance, looked at different MPS conditions, isolated cell types' contribution to the metabolism, and glucose utilization and production's dependency on insulin. And with all these partial insights integrated to our model, we felt confident to start to introduce our first M4 drug to the chip. We decided that our first M4 drug was going to be exenatide, where its expected response is well in line with the pancreatic and hepatic chip, and also its effect is well documented in vivo systems. So exenatide binds to the pancreatic GLP-1 receptor. It does many things, and among them it increases glucose-dependent stimulation of insulin secretion. So we planned an MPS study for this, where we wanted to have both liver and pancreatic cells in the MPS. We planned to first allow for some insulin resistance to develop, and then we added exenatide, so the drug, in the hopes to restore glucose utilization functionality. In this figure, we can see, once again, glucose and insulin concentrations in the MPS media, which the model, amongst many things, described. Please note here there's a change in glucose utilization over time, and we have media changes at day 0, 1, 3, 5, and 7. At day 7, however, we add exenatide, and we see a significant impact on the insulin production in our chip. If we compare the glucose utilization levels, so the glucose levels between day 3 and day 9, we see restored glucose utilization levels. And this is directly linked because we have higher insulin production here between day 7 and day 9. So in conclusion from this slide, exenatide has a significant impact on the insulin production, which we can study with our chip. We have now trained the mathematical model on the hepatic metabolism and also exenatide PD properties. We then trained the model on PK properties, and now we can use the model and wanted to see if we can use exenatide to prevent insulin resistance development. So with our new metabolic question formed, we did our initial experimental protocol, and now our model has matured, and we can use our model for our protocol planning. So we simulate alternatives of the protocol using the mathematical M4 model. We found that the different protocols had a significant impact on the metabolic outcome of the experiment. So here we can see simulations of 4 different protocols, where the blue color is a group with exenatide and red color is without exenatide. And here we can vary things such as the dosage of exenatide, media change frequencies, the amount of cells in the system, and many different things. And here we see also with exenatide, we have higher insulin production and higher glucose utilization levels. So this is one of the strengths of using mathematical modeling. So now we can compare these simulations and determine which protocol was the most suited for our metabolic question to investigate the development of insulin resistance. One simulation here resulted in a buildup of insulin resistance of 1% difference between the groups, while another protocol, I'm not sure if you see it in the corner here, but one simulation, the protocol 4, resulted in a 5.5 difference of insulin resistance development over a time period of 15 days. Our work is not only limited to use as a tool to plan future studies and get more out of the MPS, we also want to use the insights we get from MPS and use it for in vivo insights. So in our model and our work, we have metabolic knowledge of hepatic and pancreatic cells. In the translation from MPS into in vivo systems, we scale this up into corresponding in vivo properties, and then we estimate the contribution of these cells, of other cells to the metabolism in vivo. So me and my research group has published papers in describing and validated models in describing in vivo systems, so humans. So we already have models describing, for instance, muscle tissues, glucose utilization, the metabolism of adipocytes, kidneys' role in glucose homeostasis, and brain's glucose utilization. And with all these insights, we now can try to estimate how the human metabolism or rat metabolism will look like based on the metabolic information we have from the MPS. Finally, we turn off the decreasing in vitro pancreatic functionality we see in the MPS. We add an inflow into the model that allows us to take in consideration metabolic variables not present in the MPS media, but something we will see in the in vivo systems. And finally, we do some allometric scaling from in vitro proportions to in vivo proportions. So the result of this is that we can, with an uncertainty, predict how rat metabolism, or a glucose-oriented rat metabolism, will behave based on our MPS experiments. So at time 0 here, glucose is injected into the rats, and the group furthest to the left is the control group without exenatide, and this group was used to calibrate these transition equations from MPS to rats. In the middle group here, exenatide 30 picomolar per kilogram per minute, we see the highest drug response, both in data and simulation. This can be seen in the highest peak of insulin concentrations here, marked with a dotted gray line. If we further increase the exenatide dosage, we see both in data and simulation a diminishing exenatide dosage response. And this is something that we can predict because this is a phenomenon we also see in the MPS experiments. So this works as a soft validation that we can do this transition. The question is now how the transition function should look like and what we can keep from the MPS and what we have to use from the literature of rat and human metabolism. So in conclusion here, the predicted dosage response is qualitatively supported by rat data. However, we do see big model uncertainties, especially in the glucose utilization. So please remember now I said that the colored area is the model uncertainty. And this blue line here is the best prediction based on the estimation data. So the model is trained on other data. The best fit to that data is underlying the simulation, and that is what also corresponds the greatest to the data that the model has never seen and it's trying to predict. Similarly to how we predict PD in rats, we can also predict PK in rats. So here we have our digital rat again. We send in digitally exenatide in it, and we predict with the model how exenatide will disappear over time. And this is a function both of renal clearance and also degradation. So from this slide we see the model predicts exenatide concentration in rats after allometric scaling and our calibration. So the final thing I want to show you today is that we do not only translate from MPS to rat, we also try to go from MPS to human. In this figure, we can see two different colors. And this is a human study with human data. Red group is a human group without exenatide treatment. and the blue group is a human group after a 16-week of exenatide treatment. Please note here, there's a significant difference in basal glucose after a 16-week exenatide treatment in both data and simulation, and we have a more effective glucose uptake in the blue group compared to the red group, where you can see that the red group peaks much higher from the same meal. So in conclusion, our initial analysis indicates that M4 drug discovery and development can improve our current drug development in regard to long duration, high cost, and the large need for animal experiments. We, the team, thank you for your time. If you have any questions or wish to collaborate, please contact me. My contact information is at the bottom of this page, and now welcome any questions you might have. Thank you.
Thank you very much, Oscar. Beautiful work, huh? Fascinating. Are there questions?
Thank you very much. Yeah, so really, really impressive. I would just have a very concrete question about, so in one of the slides, you showed these two squiggly lines, and in one of them, I think insulin resistance developed, or the insulin levels dropped, and that was quite abruptly. So it was like for 14 days or so, nothing happened really, and then all of a sudden, a lot of things happened.
Yes.
And I was just wondering whether there's like an underlying, simple explanation for that.
Yes, so physiologically we see insulin sensitivity develops very quickly in our MPS chips. And do you mean technically why the drop is so fast, or why it happens at all, roughly by the green line?
Yeah, yes, so I'm talking about the green line, because that's like flat, right? And then all of a sudden it's not flat anymore. I was just wondering why that is.
Thank you. So during this time, we see at the glucose levels here that the glucose concentrations are within, for humans, a healthy area. And then at the last media change, so time 288 hours, we introduce a new concentration of glucose it hasn't seen before, and that is very high. And that triggers both physiologically in our model this development of insulin resistance. So because of the last change there, the glucose, we do see this quick drop at the end.
Thank you very much.
Thank you.
I saw a question over there. There we go.
So my question is about the mathematical modeling that's going on behind the scenes. Is it like a proprietary software that you have for this, or are you using some third-party softwares like, for instance, Copasi, in which you draw the reactions and then you calculate the ODEs?
So we do our own ODE modeling, like in a text file, and this can be run in Python or MATLAB or any programming software. So in this typical model has been run in MATLAB.
Okay, all right, thank you.
And we develop our own models. It's not a fixed software previously.
All right, perfect, thank you.
Great, thank you.
Another question?
Yeah, thanks. So maybe one is a comment or a question. On that slide here, so you see that the insulin curve actually drops after, 10 days. So did you check that your pancreatic islets are healthy and that they can still produce enough insulin? Because they're exposed to glucose levels that are supposedly normal and human, right? So the question is, why are they developing insulin resistance if you assume that you have a constant number of islets?
Right, so thank you for that question. The disease progression has different parts, and the insulin production part of this equation is time-based and not the glucose-based. This drop in insulin production you see in the green group is because in the chip they slowly decay and lose functionality. So that isn't really based on the history of glucose. However, the sensitivity, so not the production but the response of on the insulin, that is dependent on glucose, and that's the drop you see.
Yeah, okay. And then maybe second quick follow-up question. You mentioned that you use allometric scaling to scale sort of the MPS responses to humans, what body weight did you use to scale that up?
Yes.
Did you consider maybe other, more like functional scaling approaches?
Thank you. So we've done direct scaling, or what we mostly likely would want is to, like our equations are based on individual cells. So we want to know actually how many cells are in the MPS and how many are overall in a rat, but this is something we don't have data on. So currently we do our allometric scaling based on the surface area. So we estimate the volume of spheroids and islets in the MPS, and then we take data on how a mean organ looks in a rat, and then do the scaling. And we do about a 15% plus minus boundary there. So the scaling is allowed to be within a certain uncertainty. If you have any suggestions on how you would do the scaling, I would be very open to hear it afterwards.
No, yeah, I was going to say, indeed, this might take a little bit longer.
After the presentation, but yeah, thank you.
Is there any final question or comment for Oscar? If not, then thank you very much.
Great, thank you.